So I click on live. Hello, good evening, and welcome to an food4Rhino webinar. Today with Intact.Simulation, a new plugin for Rhino, actually updated to Rhino 8 recently. And the aim of this webinar is to show you how to run automated mechanical simulations. Intact.Simulation for Rhino Grasshopper allows users to tackle the most complex geometries without the hurdles of the featuring, model preprocessing, and meshing hurdles. And Michael Freitag is the speaker. He's the founder and director of development at Intact Solutions. He's also an experienced designer and craftsman, and he's passionate about bringing life to conceptual designs physically and virtually. He holds a PhD in mechanical engineering and a master's degree in computer science from the University of Wisconsin-Madison. And he will start with an introduction to the product, followed by a live demo. Remember that there is a chat on the right part of the screen you're watching the webinar. Please feel free to post there your questions, your feedback, and at the end of the webinar, I will pass your questions to Michael. So Michael, Rick, Neil, many thanks for being here, for your time, and for the proposal to this webinar. And we are eager to see what Intact.Simulation for Rhino Grasshopper can do.
Okay. Well, thank you very much for the kind introduction. I will work on sharing my screen here. Let's see if I go here and F5. Hopefully you're seeing my screen. Okay, I see a thumbs up, so we're going. So yes, today, thank you, Carlos, for the introduction. We're going to be talking about Intact.Simulation for Rhino Grasshopper, and let's get started with a little background first with the company. Intact Solutions is a company that was founded in 1999 as a spinoff from the University of Wisconsin-Madison. We've always had a focus on automating simulation for designers and design professionals from a range of industries, from marine to mechanical engineering to architecture. We have a long history of innovative R&D, where we work with industry and government partners to develop technologies and then develop them to a point where we can release them to the public for people, for designers and engineers and architects to use to drive their designs. So we've got this history of products, starting with Field Match, which was released in 2004. Then we've had a range of scan and solves, starting with scan and solve version 1 in 2011 and 2014, and then Pro was released in 2017. We also have an online service called Intact Design, which allows users or designers and hobbyists to upload their STL models and perform simulations within a browser environment. We also have a product that which is part of this ecosystem, which is called Intact.Simulation, which is our latest offering of mesh-free simulation for the design professionals. It uses a completely new core compared to our old software called Scan and Solve. We call this method or this new technology the Immersive Method of Moments. This I won't get into the details, but what happens is the way this works is it allows us to do simulation directly from the geometric model instead of going through the normal pains of meshing. And because of the way it works, we can actually support a wide variety of geometric representations. Intact.Simulation at the core, as a core product, is a kernel, if you will, for simulation. It's available as a C++ API, a Python API, as well as through the command line. Today, I'm going to be talking about Intact.Simulation for Rhino Grasshopper, which actually brings this functionality to the Rhino Grasshopper environment. So why do we want to do mechanical simulation in Rhino? the purpose of simulation is to predict the performance of products early in the design process. So here we see the typical design process starting from conceptual design through detailed design, building prototypes, testing, and production. What simulation allows us to do is identify and avoid design mistakes early in this design process, where 70 to 80% of the cost is actually determined at the earliest parts of the design stage, long before you get into prototyping and testing. So with simulation, you can predict how products are going to perform, hopefully before you get to the point where it gets. So it allows you to actually identify and avoid design mistakes that may occur. If you the earlier you catch them, the easier it is to repair and to reduce the cost of repairs to those designs. The worst case would be if you don't do any simulation and problems don't show up until after it's in production, which would be really expensive. So with simulation, we can do these tests early and virtually. So Intact.Simulation for Grasshopper is the successor to Scan and Solve. It's an easy to use, powerful FEA simulation tool for designers, and it still has no meshing headaches like Scan and Solve. But unlike Scan and Solve, or in addition to, I guess, as a positive away from Scan and Solve, there's Intact.Simulation has much more speed, more types of physics, more types of geometric representations that can be supported, and much more automation. And we will be going through demos to demonstrate this stuff today. So with the ability to manufacture complex geometries with additive manufacturing these days, we run into problems with simulation with the typical design or with the typical simulation workflow, which relies on meshing. Meshing is the process of breaking up the geometry into finite elements, and in order to do simulation. With Intact.Simulation, we no longer have to do this. So in the typical mesh-based workflow, the geometry and cleanup in order to support meshing is about 62% of the entire process. So it's a sort of wasted time when you could actually be spending this 25% of the time applying loads and material properties and actually running the simulation. So the problem with meshing is that with these challenging geometries that we can actually create with additive manufacturing, the mesh has to conform to the smallest feature, which is difficult in the best case and impossible in the worst. The mesh creation process is not particularly robust, and it may require manual pre-processing and manual intervention to actually generate these meshes. And so this whole process of meshing breaks automation and continuity. So it interrupts the design process and interrupts the thought process as well that occurs during design. So today I'm going to just going to demonstrate the software with three basic simulation or basic workflow setups. First with stress simulation as well as our modal simulation. And throughout the demo, I'll be showing some information on some of the advanced topics about like units. We'll also be looking into how we can leverage Grasshopper capabilities to do to use the automation capabilities in Grasshopper to affect changes to the simulation based on changes in the geometry. If I remember, I'll talk a little bit about custom materials as well as some details on various solver settings. So with that, I'm going to jump into the first demo. So with this demo, I'm going to demonstrate the basic problem setup, going from settings through specification of components, restraints, surface loads, and then some basic visualization. So if I switch over to Rhino now, here on the right, you can see Rhino. And this is the simulation we're going to be going for. This is a basic stress simulation. We've got the link fixed at one end, and we've got a load being applied to basically stretch this link out. And on the left, we see the Grasshopper setup that is actually leading to these simulation results. So to do this simulation, or to actually set this up, I'm going to start from the assumption that Intact.Simulation is already installed and Grasshopper is running. So I'm just going to wipe this out, and we'll start from scratch. So on the right, again, we see the part. which is just a link. We've got some boundary conditions, a geometry already specified. Typically, if you don't have this already specified, you would go to sorry, the window is covering. I've got a thing up here that's covering up my window. Anyway, sorry. Typically, if you start with just a solid, you would have to extract these surfaces in order to apply the boundary conditions. Is there a way actually I can get rid of this thing at the top?
I think you have the option to share a screen or a window. You know what I mean?
Okay. Oh, there
Maybe
we
if
go.
you
Okay.
stop sharing and share the screen.
Okay. Yeah. What I did is I just figured out that I can drag it's the zoom toolbar. I just dragged it off the side.
Okay.
Yeah. Thank you. So starting with, we're going to start with a blank Grasshopper canvas, and we see Intact.Simulation has been added because we ran the installer. And when we choose the Intact.Simulation menu, we're presented with the Intact.Simulation toolbar. Starting from the left, we've got different solvers, components, materials, and various stuff here. We'll go into details in a moment. So what we want to do is actually do stress simulation. So we go to the solver group of the toolbar, and we choose that a stress solver. And we'll just work our way top to bottom, specifying what we need to do. So at the top, we've got solver settings, and the solver settings are also in the solver block. So we'll just drag one onto insert one onto the canvas, and we'll use the default settings, which is a resolution of 100,000 finite elements essentially for the simulation, which is 10 times what Scan and Solve, the default setting in Scan and Solve. So I think you'll be impressed with the speed here. So we've got our simulation settings set up. Now we want to actually add components to our simulation. A component is a solid that has material properties applied that allows it to be used in the simulation. So to add our first component, we go to the component tool, which is just the icon is a puzzle piece. And the component tool takes 3 inputs. We're only going to talk about the first 2. The first is the geometry, and the second is the material. So to specify the geometry, we want to have Grasshopper refer to this link on the right. So to do that, we'll just insert this as a brep, and we'll add a brep to the canvas. We'll right-click on that brep block and set one brep. We plug that into the geometry input, and we're half specified. Now we also need to specify materials. So we go to the components and materials group of the toolbar, and we're going to specify a standard material by selecting this standard isotopic material from the toolbar. We plug this into the component tab or component block, and we're almost ready to go here. Our material, so if we right-click on the material block, we've got a variety of materials we can apply. We'll just choose gray cast iron, but we could also choose among, so we have a large variety of steels, non-ferrous metals, non-metals, concrete, architectural materials, a whole list of 3D printed plastics, as well as engineering plastics and biological materials. So we've got this single component specified, and we can just plug that into the component input. Now, we're not ready to go yet because we have to specify loads and restraints. So for restraint, we're going to restrain the light blue portion that's now highlighted in yellow on the right-hand end. And we'll do that by selecting the fixed restraint tool from the restraints and loads group. Drop one onto the canvas. And this is a surface. So we'll add one of those to the canvas, and we'll right-click. I've already got it selected in Rhino. Set one surface, plug it into the restraint, plug the restraint into the solver block, and we're down to one thing left, and that is we have to specify loads. So for loads, we're going to apply a force that is tending to stretch this away from this other end by applying a bearing load. This is in the restraints and load section, we choose the bearing load. And we're going to apply it to that surface geometry, the two surface geometries. So we add a surface to the canvas, right click, set multiple surfaces, plug them in. And this is a bearing load that's going to be distributed over the inside surface of this hole in a particular direction. And the direction is away from this hole toward this through this hole. So we have to specify a vector. So we'll add a vector to the canvas. We'll right click on to set one vector. And in Rhino, we have to choose a start point that is the center of this hole going through the center of that hole. So this is now pointed in this direction, and we'll plug it into here. For the magnitude, we'll just specify, we'll right click and set a number to 30,000. Now, by default, the units on the load are going to be in the MKS system. So this is designed in inches. Sorry for the people in Europe, but that's the way it's designed. So I can change the units on this so that it's actually pounds of force rather than newtons by right-clicking and then choosing pounds force in the load dropdown. And I plug that into the load, and we're good to go. So the yellow, I'm out of date. That's the only problem. It's fine. That was a minor update to the install. There's no functional difference. So I'm ready to go, and I can do so by hitting solve. And here the solver starts up, and we'll have results in about 10 more seconds. Maybe longer. 12 seconds, 15 seconds. So our results are, we've got a solution that's available. So the first thing we want to do is actually visualize that solution by adding a visualize tool or visualize block to the canvas. And that's in the visualization and results group of the Intact.Simulation toolbar. Now we take the output from the solver block, input into the visualization block, and we see we've got a problem, but we don't really have a problem. It says that we have to right click to select a solution quantity. So if I right click, these are the solution quantities that are available. We have displacements, the various strain components, stress components, principal stresses, von Mises stress, danger level, topological sensitivity, and strain energy density. So the first thing we'll do is let's just look at the von Mises stress. And right now we've got a little bit of interference because I'm in a shaded viewport. If I, oops. Oh, what happened to my thing? Oh, there we go. I'll switch to a wireframe viewport, and then I'll shut off the display of the from the Grasshopper side of things. So here we've got basically simulation results presented in Rhino. At this point, I guess I'll ask if there's any questions. Don't know if any have come through on the chat.
Not so far.
Okay. Yeah, please, if there's any questions, go ahead and put them in the chat, and then I'll try to address them as they come up. So in this case, I've actually got another design available. And what's interesting about Intact.Simulation versus Scan and Solve is that the geometries are, for boundary conditions, are not attached or associated directly with the geometry that is being used in the simulation. So what I can do is actually reuse these boundary conditions on a different geometry. So I can swap in a different geometry, in this case, this one, instead of the one with the T-shaped profile. I can either add a new B-rep here, B-rep, or I can just swap it out here. So what I'll do is just set one B-rep to the other geometry, and our workflow is now out of date. But if I hit solve, it will go through and run the simulation on this new design. And we see the new simulation results here. So that's basic simulation setup and operation from Grasshopper for Intact.Simulation in Rhino Grasshopper. There's also some visualization tools that we can experiment with, and we'll do that with the next example. So the next example is this sort of an architectural example. This is a concrete slab with a Voronoi set of Voronoi, I don't know, recesses underneath that are defined by, this whole shape is defined by this curve or this polyline in Rhino. So by dragging this around, I can, do some, change the shape, and it automatically updates the geometry that we're dealing with. I can change the number of cells. I'll keep it something reasonable. And it automatically updates based on the number of random seed points that are fed into the geometry. We can adjust the rib thickness. We can adjust the roundness of the cells. There's a whole bunch of different inputs here. At the moment, it looks like it's not quite working right, so I will change this to a different count. It doesn't cause a problem, it just looks bad. So the top part of this workflow forms this top slab, which is the shape based on the curve, or based on the polyline, as well as the Voronoi recesses. This part of the workflow generates the periphery of columns that are supporting this slab. And the rest of this workflow basically sets up the simulation. So for this simulation, we've got our simulation settings. We're just studying those. We're leaving those as the default. Our geometry for our component is the top slab, and I think there's 7 columns. And the material is a fairly high strength concrete. That is one of the default material, or one of the standard materials that's built in on installation. So we've got 8 components participating in this simulation. They're all made of concrete. Now, the restraint is specified by this bottom face, where this face is intersecting the bottoms of the columns. The bottoms of those columns will be restrained. We've also got a pressure load applied to the top face. I preview that to this top face, this stuff is all parametrically done through Grasshopper. And this is a pressure load of 5,000 pascals. 5,000 pascals applied over that top surface. And we also have a gravity load. So this is a volumetric load that's basically gravity pulling up, because this is a concrete slab. Weight is a particular concern with this, and with the gravity load, this allows us to actually run a simulation that incorporates that load. Now, there's also this last toggle here, or the last setting here, which is an auto mode for the solver. So right now it's set to false. So if I choose, the solver will sit and wait for me to, I have to hit solve in order to run a new simulation. But if I set this to true by toggling it, the solver will run automatically based on changes that I make to the geometry. Anything upstream that changes the geometry will be automatically incorporated into the simulation.
While the simulation is going, I would add that this auto mode is only available on our Rhino 8 compatible Intact.Simulation product.
Thank you, Rick.
Yeah, so you must have Rhino 8 to run this.
So our solution results are done. Right now I don't have them turned on, but I will turn on the preview, and we'll see them in Rhino. And I'm going to turn off the preview in Grasshopper for the geometry that led to that simulation, so that we can actually see the results. I think there's one more I need to, turn off the preview on that. So in case, I'm actually displaying the danger level for this for this concrete structure. And you can see that the danger level is high and red in these regions, which is basically anywhere the concrete is in tension. And we can see the magnitude of that danger level by looking at the outputs on visualization. So for the displayed solution component, in this case, the danger level, the output on this gives us the range of that quantity. So if I open a panel, and insert a panel, and we can see that solution quantity here. We also have inputs on the visualization to specify a deflection, so you can actually magnify the amount of deformation that's displayed. So right now there is no deformation based on the deflection, but I can plug that in. At 1,000, you can see how the shape is going to deform under the specified loads. We can also adjust solutions visualization settings, which is you can adjust the legend range as well as the legend that's actually being used. And we can also turn on cutting planes and see what the solution looks like on the inside of the geometry. So right now we've got the solver set to auto. So if I go into Rhino and select my shape, I can modify the shape. It automatically updates the workflow in Grasshopper. I'm getting a new shape. It's running in the background right now. And in a moment, you'll see that it will complete, hopefully. It's running. And it will update the geometry to the new shape as well as the simulation results. So that's the new shape with the new simulation results. We can also modify the workflow here to add an acceleration load, which is another type of load. There's all kinds of loads up here. So we're going to do a linear acceleration load, which is, say, an earthquake type load. So I add one of those to canvas, and that requires a vector, like a direction for the acceleration. So I'll just do whichever, doesn't really matter. So this is as if you're taking have an acceleration in that direction. And we're going to set a magnitude here to 9.81 meters per second. And we can actually choose different units. In this case, the default is meters per second. You can do inches per second, millimeters, whatever. I'm just going to leave meters per second. So this is a 1G acceleration in that direction. And then I'm going to shift select or shift add it to the linear, or so the volumetric loads input. So now I'm combining gravity as well as a linear acceleration load. And the simulation automatically will run and update the results. And you see that the whole thing has been shifted that way, and our distribution of the danger level has changed to reflect that new loading. Let's see, what else is there to cover? If there's no questions, I will move on to the next one, which is a modal simulation, which is a type of stress simulation which looks at the natural frequencies of a shape. I assume that if there's no questions yet. No questions. Okay. So the final example is
Actually, real quick, Michael, there's a question in the chat from Moonrabbit. Hello, Intact. I do have a question for the simulation results range. Is there a way in which we can set to specific values, for example, minimum of 50 MPa and maximum of 350 MPa? Or how does the custom range work?
Oh, yes. So the custom range on the legend is available through the visualization settings. So I'll just drag one of those onto the canvas from the visualization results. group. So this is its general purpose. So it's a little bit, I guess, a little bit hard to use, maybe a little bit more confusing than ScanNSolve is. But the legend max and min can be specified through these inputs on the solution, on the visualization settings. So I'll plug one of those in, and L max is by default is 1. So it corresponds to a maximum range of the upper limit of the solution quantity currently being displayed, which in the case of danger level is 1. And L min is sort of the position of the minimum relative to the total range. Danger level is probably not the best one to show it on, so I'll just switch it to von Mises stress. And so if I want to look at a value, so currently the maximum value for von Mises stress is 1.64 megapascal. So if I want an upper limit, say, of 0.8 megapascals, I can input, I'll put a range slider here, 1.0, 1.00. I'll set this at 0.5, 1.5, and that will set the upper limit to half of that range. So it's now our max is 0.8 megapascals. And we can also set the minimum, say 0. Set that to 1/4 of the total range by going to 0.25 and specify. So the lower limit is now 0.25. Actually, it's displayed here, 0.46 instead of whatever it was before, instead of 0.07. You can, if you want a specific value, you can do the mathematics and figure that out directly, but I don't want to try to do that in front of an audience. But that's how the minimum and max range work. So or the limits on the legend work. So it's a fraction of the full scale. Hopefully that helps. Any other questions?
Yep, that was all, Michael.
Okay, I'll move on then. So this final example is an example from Ryan McClelland at NASA that is a particularly challenging problem because this is an additively manufactured part, or it's designed to be additively manufactured with an infill that is not solid. So in this case, I've got a workflow setup that takes this mesh in. This is a surface mesh in Rhino with a lot of faces. But what I do is actually combine this, I combine Intact.Simulation with a couple of other tools in Grasshopper, third-party tools in Grasshopper, to create a model that has an infill of a lattice of struts and an exterior shell. So the top part here is we're constructing the shell of this, which is what we do is we feed the mesh into Dendro and then do some offsetting operations to construct a shell, a shell geometry in VDB format. And the lattice infill is created creating a cellular structure that sort of overlaps this shape. I preview that, you can see the cellular structure. This is courtesy of Aaron Porterfield, who created this nice plugin called I'm blanking. Crystalline.
Crystalline.
So, yes, Crystalline. So we're basically voxelizing the interior of this thing, and then we're replacing those voxels with with unit cells. In this particular one, we've got a lattice of struts where we can change the radius, and that ends up being that geometry. So we take these geometries and we can take them and feed them into a union operation. which this is a dendro union. So we end up with a, let me just take this, shut this off and turn this on. Oops, wrong one. So there's the shape that we're going to do simulation on. And then we use dendro to write this implicit representation of this shape out as a VDB format. We have our own reader that reads in the dendro VDB. So we output the dendro VDB, and we have a dendro input on our toolbar that allows you to read that file and incorporate it into simulation. So I'm going to toggle this because it doesn't automatically update, but now it should be up to date. And we've got a dendro volume here that we can actually apply our simulation to. So for this particular, in this case, we're assembling the components. There's four interface solids here that are represented in Rhino by surface meshes. And then the dendro volume is coming in here as another geometry, in a VDB type. And we're applying the material of, what is this? This is aluminum 6061 T6. This is a modal simulation. This is an upright or a bracket of some sort that is holding holding some sort of a cargo. And this shape here is part of the assembly that we're using to simulate the behavior of a cargo with a particular set of mass moment, or a particular mass properties. And we do this by actually creating a custom material here. There's some math here, but we use the custom ductile material, which is available on the components and materials section of the Intact.Simulation toolbar. And what we're doing here is that we're just sort of ignoring the Young's modulus and Poisson ratio stuff, but we are specifying the density using some math here, so that this block of material has essentially the mass properties of a cargo that we don't know anything about other than its mass. We set up a modal simulation on this to see what the vibration behavior of the shape is by using the by inserting a modal solver from the solvers section of our toolbar. And it requires just a few inputs. We've got a solver settings coming in here. I think I'm just using, the default solver settings. The components, we've got the cargo, as well as the four interface solids. So here's the cargo, and here's the part itself. And we're going to be requesting, it's restrained on the bottom, similar to the last one. It's restrained on this bottom surface, wherever that's contacting that. Oops. Don't know why it's not displaying the preview there, but it should be. So we're going to request the first 5 vibration modes of this shape. I think I've got a solution actually available here. If I turn on preview, so this is the first vibration mode. And so this is the 5th vibration mode. And downstream here, we've got actually, I'm just going to hit solve, and we'll run a simulation. So this is the interior with an infill of struts. And you'll see that it's very easy to change the geometry, or the geometric definition, and run simulation automatically. So these are the first 5 vibration modes. And what in my workflow, I'm going to set this to, actually, I'm just going to leave it alone. I could set this to auto. I'm not going to. What I'm going to do is actually replace the shell into the infill of struts with a with an interior of a gyroid interior. So here, instead of having those struts, I'm going to have a gyroid interior, which is kind of not good looking, but it's simple. So we're going to take the union of that with the shell, send it out through BD. We're going to take the union of that. So we've got the union of that gyroid lattice with the shell. Then we're going to send it out to VDB. We'll toggle this so that it updates the geometry in our simulation to use this geometry instead of the strut geometry. Again, the rest of the workflow, we're assembling the components, leave the cargo alone, and we can solve this to see what that looks like. Now, we could also put this in sort of a loop if we wanted to. That's kind of an advanced topic where we could use a data dam potentially we could actually sample the solution fields and use that to modify the geometry upstream using a data dam. Hopefully we can cover something like that in a future webinar. So here's the new set of frequencies. So the first 5 frequencies are here. And we can see that changing from a strut infill to a gyroid infill increased the natural frequency from 1290, the first node of the natural frequency from 1294 hertz to 1348. So the gyroid ends up with a stiffer structure. And with that, that's my final example. I will go back to so we've gone through the three examples. And I encourage you to try Intact.Simulation for Rhino Grasshopper. You can download a trial from our website or from food4Rhino. And that looks like this is our website. This is food4Rhino. So on food4Rhino. Our documentation, I encourage you to look at our documentation, which is this link. Here's all of the getting started, advanced capabilities, components and assemblies, talk about materials, all of the documentation is here on the web. We also have examples that you can download and try for yourself, which are also in our learning materials. Here we've got some beginner examples, advanced and benchmarking examples. And if you have any questions, please feel free to reach out to us at support@intactsolutions.com. And with that, I'll answer any questions that hopefully came up, or if Rick or Neil have any things that I did not cover, let me know, and I can maybe discuss those.
Yeah, Michael, this is Neil. Sorry.
Go on.
There's a question about do we have support for wood material as or timber material? So can you show quickly maybe how
yes. Let's make this out of wood. So let's see. So for materials, so right now I've got an isotropic material. I can delete that. And yeah, so that's one of the details here. We've got so these are the custom custom isotropic materials. These are the blue and red are the thermal materials. And then we've also got custom orthotropic materials. And then we also have standard orthotropic materials. So I'll add an orthotropic material here. So this requires, so wood has orthotropic properties. The material properties vary depending on the orientation. So we need to specify the orientation of that material. But among the standard materials, if we right-click here, we can see we've got uniaxial composites, quasi-isotropic composites. We also have these are the woods that are available. This is about the only woods that are available. It's hard to get because wood is complicated and it's hard to test. So it's hard to get it's hard to find a lot of standard materials for wood. But these are the ones that are built in. So I'll just choose, it doesn't really matter. I'll just choose walnut, I guess. And by default, the orientation of the wood is aligned so that the long axis of the wood goes along the x-axis. The y-axis of the wood is through the rings, and the the y-axis is tangent to the rings, and the z-axis is through the radially through the wood. So that would be a wood that's facing this direction. Now I really want the wood to be probably facing this direction. The easiest way so what we need to do is actually create a transformation that rotates the wood into an orientation that makes sense like that. So let's see, the easiest way to do that is probably to create a rotation.
We have some examples too, in our wiki.
Okay, yeah, so this is a rotation about an axis at this moment. At the moment is 90 degrees about in the world XY plane. And if I actually display that, I think the local x-axis is pointing of this transformation is pointing along the axis, so I can plug that in here. And if let me just test something here. It's probably correct, because I'm rotating 90 degrees from X this way into this, and it's rotating in the XY plane. So that simulation is set up, and I can hit solve. Or that material is set up, and I can hit solve. That's kind of an advanced technique, it's an advanced topic. And there's techniques you can use to sort of visualize that orientation a little bit better. Like you can, if you draw, if you insert something that's pointed, say, along the x-axis, like a cone or something, you can apply a transformation, for example, or oops, let's see, I'll add a cone from the origin this way, perspective this way. And we can transform this geometry using this transformation that gives this, so you can see that it has oriented it in this direction. So here you can see, so we've actually got simulation results available here as using wood as a material. So the values of stress. Yeah.
There was another question about what kind of joints or we have. So you can talk about that a little bit.
Yeah. So joints, we don't do joints per se. We do have partial restraints if we choose a displacement boundary condition. Oh no, that's this one. So we got tangent sort of boundary conditions where you can specify that a particular face remains, it slides, the face is allowed to sort of slide along its tangent to its surface. So if I were to insert one of those, I can specify, say, if I want this surface to maybe only slide along its tangential, or along its plane, what I can do is I can set a boundary condition on that edge, and so I'll do, or sorry, on that face, and choose this surface. And what I'm doing now is extracting that surface and making a copy of it so I can apply a boundary condition. You could also use Grasshopper to select these faces, but this is the easiest workflow to just do it visually or manually by hand. So if I'm going to reach per to that surface, so set one surface and apply a boundary condition so that geometry is now, that face can only slide basically along its surface. So that's considered a load. So I will add that to the load input with the shift addition to the load input. And if I click solve, it's going to go off and solve. And this face will now remain on that plane. And you see the results have changed. So it's, this site is now, if I look at the displacement, I think, yeah, this is displacement total. The displacement is moving along this plane on this particular face. This one is still moving in the normal, in the expected direction.
Cool, thanks.
Yeah.
And in general, we support like bonded joints, right? Like for multi-material assemblies.
Right. That's a good point. So anywhere you have multiple components, for example, this one, anything, these are separate solids. The columns are separate solids. The slab is a separate solid, but anywhere they're in contact is basically treated as bonded. So
I don't see any
other
other questions. I don't see any other questions in chat.
Yep, please feel free to reach out to us with any, via support, the support email if you have any questions or what.
You answered already this one about fatigue analysis, right?
Oh, no, I didn't see
It's a
that.
new one.
So the question is, can we do fatigue analysis right now, Michael?
Not fatigue as a topic, not directly. If you know, you can use the capabilities to, or use simulation to help you with fatigue. So if you know the maximum and the minimum loading and the cycles, you can use the simulation tool. You can use Intact.Simulation to look at the stress variation from the maximum loading to like the minimum loading if you've got cyclical loading. So we don't support fatigue directly, but you can use it to inform a fatigue analysis. Is there a particular topic on fatigue, that a particular application of fatigue that I guess it may be of interest? So that may be of interest so that you can inform us, let us know, because it's it's certainly a capability we can, if there's enough interest, we can look into adding it.
I guess there is also a forum on your website, right? Or an email, support email.
I think we are using the McNeel forum.
Right. So there's a
discourse.
Discourse,
Yes.
yes.
Discourse,
There's
Actually, I think I created it, right?
Yes, yes. So there's any questions, feel free to post there as well. We're always monitoring discourse.
Perfect.
Or reach us on LinkedIn too. Like we're very active on LinkedIn, posting all kinds of fun stories and about our technology.
Nice. So it was an amazing presentation. I'm glad to see this kind of applications inside Rhino. Many years ago, it was we couldn't think about something like this in Rhino Grasshopper. I think, both product designers, mechanical engineers, architects can benefit a lot from your technology without having to know so much about FEA as an engineer that dedicates to that all day long, right? That's the aim, no?
Right.
And very fast results as well.
Right.
Okay, many thanks. I think you cover all the questions. Aaron Porterfield, also thanks to you, Michael and Neil, for mentioning
Thank you,
him,
Carlos.
your example. And this webinar is being recorded, so if any of the viewers missed the beginning, just refresh the YouTube page or look for the food4Rhino webinar series, and you will find it there. Thanks, Neil, Rick, Michael. Hope to see you soon. And enjoy the rest of the day.
Thank you.
Thank
You
you.
as well.
Bye-bye.
Thank you, everyone.
Bye.
Bye.